Our planet is haunted. Now you might think that is an odd thing to claim for an astronomy channel. But there have been whispers among astronomers that something is out there. Ghostly specters lurking in our orbital path. Entities that have eluded scientific detection for decades, drifting in perfect balance between cosmic forces. Some claim to have captured faint images of these ethereal silhouettes, looming up to 9 times wider than Earth itself. Yet others have searched the same regions of space and found nothing at all. For over 6 decades, astronomers have debated their existence. Are these mysterious entities merely elaborate optical illusions? Or something truly extraordinary hiding in plain sight? What celestial phenomenon could simultaneously be so massive yet remain so elusive? Is the moon truly Earth's only companion in our journey around the sun? Today, we're investigating one of astronomy's most enduring mysteries, the controversial ghost moons that may be silently accompanying our planet through the cosmos. This ghost story begins in 1961, when Polish astronomer Kazimierz Kordylewski first spotted 2 diffuse patches of sky that kind of looked like clouds through a telescope, which were located suspiciously near the stable L4 and L5 Lagrange points of our Earth-Moon system. In case you aren't familiar with Lagrange points, let me quickly explain. Lagrange points are positions in space where the gravitational forces of 2 large bodies are balanced by the centripetal force required for a smaller object to move with them. This creates a sort of gravitational equilibrium that allows the smaller objects to maintain a position relative to the 2 larger bodies. Lagrange points were named after the Italian-French astronomer and mathematician Joseph Louis Lagrange, after he published a prize-winning paper about this phenomenon in 1772. While we're going to be talking about the Lagrange points present in our Earth-Moon system in this video, similar points exist for other 2-body systems, such as between the Earth and the Sun, or Jupiter and the Sun. In any 2-body system, there are 5 spots where gravitational forces and orbital motion create these Lagrange points, and they're labeled L1 through L5. 3 of these, L1, L2, and L3, are considered unstable. Small objects may be temporarily captured near these points, like the NASA ESA satellite SOHO at L1 or the James Webb Space Telescope at L2, but they have to make corrections to their altitude and course every 23 days to avoid drifting out of position. Objects in these unstable equilibrium points are balancing on a metaphorical knife's edge, and any slight push from the solar wind, radiation, or the moon's gravity will tip the balance. But L4 and L5, these positions are stable. Unlike the other Lagrange points, these each make equilateral triangles with the Earth and Moon, and are resistant to gravitational perturbations. Because of this, objects like asteroids and dust tend to accumulate in these areas. And that's where our story picks up. Kordylewski's observation of these ghostly faint clouds, originally named libration clouds, but since renamed Kordylewski dust clouds, or KDCs, in the L4 and L5 Lagrange points, ignited a scientific debate that has lasted for decades, one that is still going on to this day. Immediately following his observation, other astronomers, both professional and amateur, attempted to locate these supposed clouds, but for years, nobody else could find them. At the time, observational techniques were far less advanced than today. Many astronomers questioned whether these dust clouds were real or merely optical illusions. After all, detecting such faint structures against the darkness of space was a challenging proposition. That skepticism persisted for years. Every now and then, an astronomer would catch a glimpse of a dust cloud in one Lagrange point or the other, and sometimes clouds would be visible in both locations. A few astronomers, including Kordylewski himself, captured photographs of the clouds, but for years, the dust clouds appeared so faint in the photos that they could not be reproduced in newspapers. These photos aren't like photos we're used to either. Images of these dust clouds have to be taken using photometric techniques, which involves glass photographic plates with long exposure times to capture the faint lights of distant celestial objects. They aren't of Hubble telescope quality. They serve more to identify changes in light intensity, and this is what astronomers would use as evidence of the cloud's existence. In 1966, NASA organized an airborne observation mission from its Convair 990 jet laboratory, operating far from city lights at an altitude of 12,000 meters. The astronomers on those 4 NASA flights were able to identify Kordylewski dust clouds in both the L4 and L5 Lagrange points, even managing to photograph the dust cloud at L5. The Orbiting Solar Observatory, OSO6, also observed the clouds in 1966, and subsequent work was published measuring their brightness and size. However, in 1976, another astronomer named Siegfried Rösser at the Max Planck Institute for Astronomy used numerical simulations to show that conditions were unfavorable for dust to accumulate in the L4 area, and questioned whether or not these clouds actually existed. Most of the KDC skeptics believe that the gravitational perturbation of the Sun, solar wind, and other planets have too strong of a destabilizing effect on the L4 and L5 Lagrange points for KDCs to be maintained. Additionally, radar studies of the clouds around this time had produced negative results, leading many to believe there was nothing of circumstance at the Lagrange points. These doubts were further reinforced in 1983, when observers using a 61-centimeter telescope near Tucson, Arizona, found no such clouds in either L4 or L5. Yet just a few years later, in 1989, the clouds were photographed again by astronomer Maciej Winiarski. From an astronomical observatory in the Bieszczady Mountains in Poland, Winiarski observed the KDCs to be a few degrees in apparent diameter. These were also the first 3-color photometric observations of the clouds, and they revealed that the clouds appeared much redder than the counterglow, which is the sunlight that gets scattered by the general dust particles in space. This observation suggested that the dust in the KDCs is significantly different in composition to other local space dust, which begs the question, where are these apparitions coming from? But then, once again, the existence of KDCs was brought into question when in 1991 the Japanese Haiten space probe did one loop around the L4 and L5 Lagrange points in an attempt to detect dust particles, but didn't manage to find any. However, astronomers say that this should not be taken as evidence against the dust clouds, as Haiten was only able to do one loop around each Lagrange point. And if the clouds do exist, the dust was likely moving too slowly for it to be picked up by Haiten's dust detectors. So, as you can see, the scientific debate that began in 1961 after Kordylewski's initial observation is one that has continued through the decades. But now scientists seem to have made a breakthrough. In 2018 and 2019, astronomer Judith Slies-Balog and physicists Gabor Horvath and Andras Barta were able to present clear evidence of the L5 KDC by examining how the dust creates patterns of scattered polarized light. To do this, they used a type of photography called polarized imaging, which uses a series of filters that can show light bouncing at specific angles. When light hits these dust particles, it scatters differently depending on the specific composition and arrangement of the particles, offering clues to the nature of the clouds. After collecting a series of images through various polarized filters, the scientists found that the patterns of polarized light in the images matched theoretical predictions for what we would expect to see from sunlight that was scattered by dust clouds. What's more, In their 2018 paper on the observations, they said that in fact, these results meant that the scatters cannot be anything other than dust particles. To back up these observations, they were able to further understand their formation of the clouds at L5 through the use of computer simulations. They calculated the motion of 1.86 million dust particles to see how dust in that region of space might behave, and found that under the right conditions, that dust could get trapped at the L5 point and remain there for a long time. The result of these simulations were dust clouds that mirrored the shape and size of what had been observed by the polarized imaging. Very small particles spread over a large area. So what's going on here? Why could some astronomers see these dust clouds and photograph them, while others claimed they didn't exist at all? The answer may lie in the structures themselves. Despite spanning roughly 100,000 kilometers by 70,000 kilometers, which is almost 9 times wider than Earth, the total mass of the dust clouds is supposedly extremely small. Not to mention, the particles themselves are likely micron or submicron sized, a similar size to many bacterial cells, according to observations from the polarized imaging of L5. A micron is already a very tiny measurement, at 1/1,000,000th of a meter. Individual particles of this size are only visible through a powerful microscope. Not only are the KDCs composed of these micron or submicron dust particles, sparsely spread across a wide area and nearly invisible to the naked eye, but the recent models made by Sleesbalog and Horvath in 2018 suggested that the shape of the L5 dust cloud also appears to be dynamic. The models point to the structure being non-uniform, with particle density varying across the KDC and changing over time in synchrony with the Moon's orbital period. This could also support the idea that KDCs are not a stagnant accumulation of dust, but rather that they may be continuously losing and refreshing their contents, kind of like an ever-evolving dust storm, rather than a fixed, stable cloud. Things like solar wind or gravitational pull from the Sun or other planets may disrupt the delicate equilibrium that holds together these dust clouds, causing them to disperse before reforming again. This combination of extremely tiny particles that are dispersed over a large area, and the possibility that these clouds that may form, disperse, and reform again and again over time, could help to explain the discrepancy in observations over 3 decades. However, the tentative confirmation of the L5 KDC in 2018 still leaves open the scientific debate as to whether these clouds exist continuously or whether they appear and disappear, depending on the influence of the Sun and other planets. Plenty of questions remain about Kordylewski dust clouds, but one thing is certain. These observations are not just a mirage, but a real phenomenon within our Earth-Moon system. Even though aspects of their structure, evolution, and composition remain under investigation, there is broad acceptance that KDCs are worthy of further study. While these so-called ghost moons that orbit in the Earth-Moon Lagrange points may seem otherworldly, our planet is no stranger to additional moons. In fact, Earth has had several mini-moons and quasi-moons before, albeit very different from the KDCs. For one thing, mini-moons typically come and go within a year, while the gravitational traps, or Lagrange points, which are theorized to cause these Kordylewski dust clouds, have existed since our Earth-Moon system formed, making the KDC phenomenon potentially billions of years old. Another distinct difference is that mini-moons and quasi-moons are solid objects, whereas dust clouds are, of course, clouds of loose dust. Quasi-moons get their name because, from one vantage point, they look as if they are true moons orbiting the Earth. However, with a wider view, these turn out to be asteroids orbiting the Sun, Mini-moons, on the other hand, are objects that really orbit a planet. They tend to be quite small and difficult to detect, which is probably why we've only ever managed to identify 4 mini-moons, none of which are orbiting Earth anymore. Take, for example, the mini-moon called 2020 CD3, which I discussed in a previous video. This small natural satellite was captured in Earth's orbit between January 2019 and May 2020, temporarily giving our planet a second moon. Well, mini-moon. In my opinion, our planet's possible ghost moons are perhaps the most exciting of these obscure types of moons because of how unique they are. Despite being dynamic structures, these dust clouds are a long-term feature of our Earth-Moon system, and we still have so much to learn about them. Observing these dust clouds has tested the limits of our observational abilities, and as our technology and science improves, so can our understanding of KDCs. We should aim to build up more observation data of the L4 KDC, as this feature has historically underrepresented compared to the cloud at L5. We could also resurvey the clouds using methods like radar to see if technological improvements can yield different results compared to the negative detections of the past, as this would further establish the presence of these elusive features and fend off any lingering skeptics. But now that they've been broadly accepted by the scientific community, future research can begin to explore how KDCs are replenished over time, their potential impact on space weather, and their influence on satellite operations. Whether KDCs exist continuously or appear and disappear over time, at least now we know that something really is out there, and we can study them with the right focus. These ghostly dust clouds continue to haunt our skies, reminding us that even the faintest, spooky traces of cosmic apparitions can hint at something palpable and worth investigating.